You may not have thought about it, but in fact, not so long ago, humanity didn't know whether there were any planets beyond the solar system. Now, thanks to modern technology, the situation has changed significantly. We know about 5,300 exoplanets outside our planetary system. It's a vast field for research. At the beginning of studying objects beyond the solar system, the first ones we discovered were large planets, gas giants. And then over time, and with the development of technology, we began to see exoplanets that in many ways are similar to our own planet. Around 50 have been found so far. In fact, right now we don't know of that many planets located in the habitable zone, which in theory allows life to emerge. However, the situation is changing. Space is gradually unveiling its mysteries to us. That's why we are discovering more and more worlds where living organisms could potentially appear. What are these worlds? Hubble? In the Milky Way galaxy, there are small systems with stars at their centers that are very similar to the Sun. Despite this, it's unlikely to find a habitable planet in these systems because most of the objects there have extremely high temperatures. However, if the main star of the system is cooler, then the habitable zone is located closer to the star itself. And at a distance of 23 light-years from our planet, in the constellation Scorpius, there is a triple star system called Gliese 667. What is remarkable about it is that in the habitable zone of one of the low-mass stars, there are several rocky planets where life could potentially arise. This is the first discovered system with such a feature. Gliese 667 has 3 stars. The largest one is called Gliese 667a, and it belongs to the K-type main sequence stars. The luminosity of this star is 88% lower than that of the Sun, while the mass of Gliese 667a is 73% of the Sun's mass. The second star in the system is the orange-red dwarf Gliese 667b, which is also a K-type star, and its luminosity is 95% lower than that of the Sun. The third star, which is of particular interest to us, is called Gliese 667c. It belongs to the M-type red dwarfs, and its mass is 1/3 of the Sun's mass. The luminosity of this star is very low and is just a little over 1% of the Sun's luminosity. It may seem like a dim, cold star, but it actually has a relatively large number of planets. Early studies of the Gliese 667c system suggested it had only 3 exoplanets. However, over time, as more information was processed, it turned out that there are actually 6 planets. And the most interesting thing is that half or even more of them may be suitable for life. And here we're talking about 3 or 4 planets. Just think about that. Such planets can be called super-Earths or mega-Earths. These are planets whose mass is an order of magnitude less than the gas giants Jupiter and Saturn, but still greater than Earth's. A super-Earth can form an atmospheric layer, which may create favorable conditions for the emergence of living organisms. The planets themselves formed mainly from rocky materials, sometimes with some admixtures of ice. We will take a closer look at the closest planet to Gliese 667c, called Gliese 667cb. Its orbital period around its star is 7 days. The planet's mass is more than half greater than Earth's mass. The atmospheric layer of Gliese 667cb is very dense and it's extremely hot on the surface. The temperature there is about 200 degrees Celsius. Planets where life could potentially arise are located farther from their star. They also have more mass than Earth. After Gliese 667cb comes the planet Gliese 667cc, and it is located at the beginning of the habitable zone. The planet completes a full orbit around its star in 28 days. The mass of Gliese 667 cc is almost 4 times greater than the mass of Earth, and its radius is almost twice as large as that of our planet. The Earth Similarity Index is 0.85, which is a very high value. Since the star Gliese 667 cb has rather low luminosity, the habitable zone is close to it. That's approximately from 0.1 to 0.23 astronomical units. For example, Earth is located at a distance of 1 astronomical unit from its star. If the Sun were an order of magnitude dimmer, our Earth would be a solid glacier. In the case of Gliese 667 cc, its distance from its star is about 0.12 astronomical units. Most likely the planet is in tidal lock, which means it will always face its star with the same side. This will have a significant impact on the exoplanet's climate, since there will be sharp temperature differences between the illuminated and dark sides. Despite the fact that the amount of light Gliese 667 cc receives is less than what Earth gets, it is compensated by the infrared range. There may be enough energy for the climate to still be more or less comfortable for living organisms. At the same time, we don't know if the exoplanet has an atmospheric layer. If it turns out that it does, we will need to find out its thickness and density. Based on this data, we could find out the approximate temperature on the surface. Let's assume that the supposed atmosphere of Gliese 667 cc has the characteristics of Earth's atmosphere. Then it would help to more or less smooth out the temperature fluctuations caused by being in tidal lock. Well, that's pretty good. While being in the Gliese 667 C star system, you would be able to see both Gliese 667a and Gliese 667b. Although they are about 230 astronomical units away, there are still some issues with the main star of the system. Unfortunately, powerful radiation flares can occur on the star Gliese 667c. Considering the fact that the exoplanets are close to their star, all these processes can negatively affect potential life on Gliese 667 cc. But the probability itself, the very process of the origin of life on an exoplanet, is also directly influenced by the mass of the exoplanet itself. And that's because the mass determines what the gravitational acceleration due to free fall will be. More massive rocky planets will have greater gravitational acceleration, which implies more massive objects on the surface of the exoplanet. The same goes for the atmosphere. The greater its mass, the higher the atmospheric pressure. And living organisms, if any ever appear on Gliese 667 cc, or if they already have, will most likely not resemble those on Earth, since they will develop under different conditions. A completely new, amazing world. Let's also talk about other potentially habitable planets, namely Gliese 667 ci and Gliese 667 cif. They're even farther from their star, and it would be logical to assume that there is no chance for life to arise there at all, since the energy they receive simply wouldn't be enough. However, if the planet's atmospheres turn out to be very dense, this increases their chances of being habitable, since heat would be retained there much longer. In general, it's a huge stroke of luck that we were able to find a system with so many planets potentially suitable for life. In the solar system, it's only Earth, but here, there are as many as 3 or even 4 planets. Let's take a closer look at what actually makes a planet suitable for the emergence of living organisms. First of all, it's an adequate amount of light, which is necessary for forming an optimal climate. We need to determine at what distance a planet should be so that the amount of light it receives is just right, not too much and not too little. We define the habitable zone, which actually means 2 boundaries. In the case of the Gliese 667c system, the inner edge of the habitable zone is located at about 0.126 astronomical units, while the outer edge is at 0.251 astronomical units. On exoplanets that are located exactly in this zone, there could be liquid water, which of course is also important for the emergence of life. If a planet is located at the inner edge, there is a risk that water will evaporate quickly and a greenhouse effect will occur. If the object is at the farthest edge, its surface may be completely covered with ice. That's why, when it comes to the formation of potentially habitable planets, balance is needed. At the beginning of the video, we said that the Gliese 667c system has 6 planets. However, in 2013, research suggested that there might actually be 7 planets. The possible 7th planet was named Gliese 667c. At the same time, it is most likely located outside the habitable zone, closer to its main star. And that means, due to excessively high temperatures, there is no place for living organisms there. However, we still have 3 or 4 potentially habitable exoplanets in the system. With the development of technology, the emergence of powerful telescopes and research probes, more and more opportunities are opening up for us to study space. And we are confident that ahead of us there are still many planetary systems with planets suitable for life. Imagine we have learned that a huge meteorite is approaching the solar system. It's heading straight for Earth. Its size is actually comparable to that of Pluto. The unknown object should be studied. That's why when the meteorite crosses Saturn's orbit, a huge number of small probes are sent toward it. However, they did not find any minerals or useful elements on the object. At the Space Security Center in Alaska, they are setting up a special laser that will turn the meteorite to dust. And now nothing is left of the meteorite, except for the video footage of the scientists who work on Jupiter. And they decided to record such an event. In short, this is what our life would be like. If we became a Type 2 civilization, we could easily deal with any threat to our existence, and we would have endless supplies of energy at our disposal. But is everything truly as perfect as it appears? And what could bring an end to a Type 2 civilization? What do we need to become a Type 2 civilization? Based on the Kardashev scale, we need to learn how to get energy not only from sources on Earth, but also from the Sun. However, it's important to note that we're not talking about just any solar power plant, but about an entire system that needs to be built. About the Dyson sphere. It's named after Freeman Dyson, a professor at Princeton University who first proposed this idea in the 1960s. A Dyson sphere is basically a huge artificial shell around a star. Its main function is to collect the energy of the star, then transform it into electricity. At the same time, part of the energy is converted into infrared radiation. The radius of such a sphere is about 1 astronomical unit, and the thickness of the structure itself is about 3 meters. What are the pitfalls here? In short, anything can go wrong. Absolutely anything can happen here. First of all, the Dyson sphere needs to be built out of something. And for that, you need an incredibly huge amount of resources, specifically from 1.5 to 10 to the 24th power tons of materials. To give you a sense of scale, that's about the same mass as the gas giant Jupiter. Where can we get that amount of materials? Well, first of all, we can dismantle a few rocky planets as well as all the asteroids we can reach from our planet. However, that's not all. The materials have to be very, very strong so that they can withstand the truly destructive energy of the sun. And the structure has to be in the shape of a perfect sphere, otherwise it will be destroyed by gravitational forces. Let's imagine that we've actually built a Dyson sphere. In this case, the difficulties won't leave us. In fact, quite the opposite. For the whole mechanism to work the way we need, the star must be perfectly centered. If, under the influence of some external factors, the sun shifts to the side, the sphere will also start to shift and will be destroyed. Well, this means that building such a massive structure as the Dyson sphere is impossible for us, and that people have misinterpreted Freeman Dyson's words. He proposed not a solid sphere, but a group of special satellites and other special devices that cluster around the star. They would collect solar rays and then transfer them to Earth. Agree, it's more realistic and sounds quite feasible. For this, we need to invent and integrate wireless energy transmission technologies on Earth. Even though there should be many satellites, we'll still need much fewer materials than for a solid sphere. We can create not only a Dyson sphere, but also the so-called Dyson bubble, a group of devices with special solar sails that fly around the star. A Dyson shell is another option where people could live, and there are actually several possibilities. However, no matter which technology we choose to develop, we will still face many problems. We mentioned that a swarm of satellites would require less material than a solid sphere, but there still isn't enough material on Earth. The only optimal option for us in this case is to look for resources beyond our planet. It's one thing if we destroy a few small asteroids for this, but it's a completely different matter to dismantle an entire planet piece by piece. It could even threaten the destruction of the entire solar system. Nevertheless, even if we did build a Dyson sphere, it wouldn't be able to deliver solar energy beyond our planet, and that would greatly reduce the chances of colonizing, for example, Mars in the future. Another important point is that a Dyson sphere can only store about 10% of the energy that the sun emits every second. This amount is still enormous, and it's 40 trillion times greater than humanity's daily energy consumption. So this amount of energy needs to be stored somewhere. One option is to convert it into antimatter. However, we don't know how to do this yet, which presents us with a whole new set of challenges. It seems that on the path to creating a Dyson sphere, we face difficulties at literally every stage. Let's set these issues aside for now and imagine what would happen if humanity became a Type 2 civilization. We would clearly be using an order of magnitude more energy than we do now, since a significant portion of it would go toward exploring and developing objects in the solar system. We would have the opportunity to mine resources in the Kuiper Belt, and of course to colonize Mars. With new materials, we would be able to create much stronger spacesuits with enhanced protection against solar wind and radiation. We could also integrate new materials into medicine, instantly fuse bones, strengthen the skeleton, and change skin and eye color. Type 2. Civilization can forget about the gadgets we're used to, like smartphones and computers. We would have a small chip that would allow us to actually use the internet with the power of thought. This means that information would become even more accessible to us. For a Type 2 civilization, the approach to security systems would also change. Asteroids and meteorites would no longer be a danger to us. On the contrary, we would be able to obtain many useful resources from them. If some object still becomes a threat to our planet, we will have weapons that can quickly and effectively eliminate the danger. With such weapons, we would seem all-powerful. But if representatives of another civilization come to visit us, it will most likely mean a death sentence for us. If an extraterrestrial civilization has approached us, it means that they have reached a type that allows for interstellar travel. A civilization can harness energy beyond its planetary system. For a Type 3 civilization, our Type 2 civilization would just look like a bag of resources that can't put up any resistance. So what should we do in that case? Make sure that no one finds out about our existence? However, get ready to be disappointed, because that's impossible due to the presence of the Dyson sphere. It's hard not to notice the operation of such a structure because of the infrared radiation it can emit. Our scientists are already studying sources of infrared radiation in order to search for signs of Type 2 civilizations in the future. A Type 2 civilization, which is not capable of intergalactic travel, may still find a way to avoid a grim fate at the hands of a Type 2I civilization. However, in that case, we would be escaping together with the entire solar system. In the future, although it is very, very distant, we may be able to build a much larger structure than a Dyson sphere, a stellar engine. It will make the sun as well as all the planets move in a specified direction. That would truly be a massive undertaking. Scientists are proposing many options for how to implement this in practice. However, the most intriguing solution to the problem was proposed by scientists Martin Rees and Seth Shostak. They suggest that representatives of the civilization type transfer their consciousness into a special system of smart dust particles that contain nanoelectronics. In this way, we could exist in all corners of the Milky Way. All of this sounds like the plot of a science fiction novel, but astronomers talk about it absolutely seriously right now. It still seems unbelievable to us, but someday this might become commonplace for humanity. The future is a delicate matter. It's within our power to bring it closer. Will the solar system become our playground? Will we be able to become a Type 2 civilization? Have you heard the expression, movement is life? If so, you probably thought it was about physical exercise. That's right, but not quite. Today we'll talk about a type of movement that's not obvious to people, which happens even when we're lying on the couch watching our favorite video, or sleeping or sitting in class. Even right now, while you're listening to this, humanity is rushing through the dark depths of space at incredible speeds. But let's take it step by step. We'll start with the Earth and the solar system as a whole. Our planet rotates around its axis. You might have learned about this back in 4th grade geography class. And this speed is not small, 1,674 kilometers per hour. The only 2 points where a person is free from participating in this wild race are the 2 poles of the Earth. The planet never stands still, and that's wonderful because if it stopped even for a second, we wouldn't exist, nor would anything else. The laws of physics are harsh, so if the braking happens suddenly, we won't even have time to realize what happened. Everything that isn't fused with the geoid called Earth will be instantly swept off the surface, and whatever remains will be washed away by giant tsunamis, because the oceans will keep rotating for a while due to inertia. These are only the initial consequences. Eventually, Earth will become uninhabitable. By the way, every 5 years our planet goes through cycles of slowing down and speeding up. During these periods, it causes earthquakes and other disasters. But does the Earth only rotate around its own axis? No, it tirelessly revolves around the sun, which is why we can enjoy the changing of the seasons. Its speed is 30 kilometers per second, which is 108,000 kilometers per hour. As you know, the planet completes a full circle in 365 days. And what else can be said about the movement of our parent star? In the images, we see static movement, dynamic planets revolving around it, but that's an exaggerated picture. The Earth and other planets, although extremely small compared to the Sun, still exert a gravitational influence on it, especially the giants Jupiter and Saturn. Every system similar to the solar system has a barycenter, that is, a center of mass around which all participants in cosmic motion revolve, including the sun. The barycenter is not constant, and sometimes it shifts a bit, moving out from under the star, where it spends most of its time. This happens when Jupiter and Saturn line up. During such periods, the sun starts to move a bit differently, which in turn affects Earth's orbit. But the nuances of our stars and the planet's movements are just a walk in the park. And now let's move from the basics to more complex things and observe how the solar system, the Milky Way galaxy, and other distant clusters move. In this case, the speeds are much more impressive. The solar system is located about 8 kiloparsecs, or 26,000 light years, from the center of our spiral galaxy. Inside the Orion arm, it's almost on the outskirts. However, its position is unstable, since the solar system is constantly moving both relative to the center of the Milky Way, where a supermassive black hole is lurking, Sagittarius A, and in comparison to other stars. Indirect calculations show varying speeds toward the constellations Lyra, Hercules, and nearby stars. The sun is moving at a speed of 15-20 kilometers per second, but relative to interstellar space, the speed of our star is already 25 kilometers per second. And the point it is heading toward, that is the apex, is also shifting. But that's not all. Just as the Earth revolves around the sun, our star also revolves around the center of the Milky Way, or more precisely around its depths, the barycenter. At the moment, the sun is moving toward the constellation Cygnus at a speed of 200 kilometers per second. To make a full circle, the solar system will need 220 million years. This is a galactic year. Just think about it. When was the last time our planet was on the opposite side of the Milky Way? There was only one supercontinent on Earth, Pangaea, surrounded by the oceans, Panthalassa and Tethys, and dinosaurs were just beginning to inhabit the land. Is it true that the solar system is gradually drifting into the maw of the black hole at the center of the Milky Way? Yes, but not exactly. First, it's worth saying a few words about circular orbits, along which stars and planets have been revolving around more massive structures since their formation. Over time, nearby objects slightly disrupt their orbits. For example, under the influence of gravity, the sun moves simultaneously in different directions, forward, upward, and inward toward the galaxy at different speeds. This naturally affects our star's motion vector as it moves through the Milky Way. It might seem that if the sun shifts slightly toward the center of the galaxy every millennium, then over time our planetary system will be swallowed by the supermassive black hole, Sagittarius A, but that's an illusion. Instead of moving in a circle, the sun follows an elliptical orbit this way. Since the mass of matter in the Milky Way is distributed evenly, our star can't revolve along the same orbit, changing it slightly each time. That's the reason for such vector changes. Do you think that's all the information about the movement of our star? No, because earlier we mentioned that, among other directions, the sun is shifting slightly upward, meaning it's rising a bit above the disk of our galaxy. So we'll soon say goodbye to our vast stellar home. The Milky Way is a massive formation, so leaving its boundaries isn't that easy. In a few 100 million years, we'll rise quite high above our galaxy, about 300 light years, but after that, the sun along with the planets will start descending back to its previous level. If you represent the process schematically, it would be an eternal cyclic, wave-like movement along variable orbits, occurring once every 60 million years. Some astronomers link such jumps to mass extinctions that occur on Earth, so maybe our galaxy, right? Scientists estimate that the Milky Way will collide with Andromeda, as our galaxy is currently moving toward it at 150 kilometers per second. As a result, a new huge formation called Milkomeda will be formed. But the deeper we go into the universe, the higher the speeds and the larger the objects become. The Milky Way is part of the local group of galaxies. Where is this cluster moving? At a tremendous speed of about 400 kilometers per second, it is flying toward the enormous Virgo cluster. But that's not its main destination. You've probably noticed that everything in the universe is attracted from smaller to larger objects and revolves around them. So how big must the object be, the one that everything we can observe, even with the most powerful telescopes, is moving toward? It turns out that all galaxies are drawn toward one single monstrous object. This means that the migrant galaxy is considered the most in the universe. The second era, the Milky Way to the instrument. Us? It's no wonder that we can only guess what this monster looks like. But the fact that the vector of movement of everything we know is directed exactly at it is a relatively proven fact. Considering the incredible mass and size of the Great Attractor, it's no surprise that it gradually pulls in smaller objects. It is believed that superclusters are the most significant clusters in the universe. In any case, we haven't discovered anything bigger so far. The macrocosm is quite a dangerous place. Even our own galaxy cannot guarantee safety for Earth and the solar system. At any moment, a supernova could explode nearby, or a large object could come from nowhere and collide with our planet. In addition to all that, we are rushing at incredible speed into nowhere, toward the mysterious Great Attractor, cutting through the boundless, inky desert called the universe. Have you ever felt like dropping everything and going somewhere far away? Perhaps soon, all of humanity will be visited by this reckless thought, since the prospects for our species' survival on planet Earth are noticeably worsening. According to scientists, the sun has about 5 billion years left. That's a long time, so we have nothing to worry about, or do we? Even in the near future, events could occur that would force us to pack our things and frantically shove them into the cargo hold of a space shuttle. And we're not talking about moving from one city to another, but much farther than that. Where can we go from our own planet? The scientific community is working hard on this. Let's not mention Elon Musk and his unfulfilled Mars colonization plans, since everyone is tired of hearing about him. There are more interesting goals. While the innovative James Webb Telescope peers into deep space in search of exoplanets, there are celestial bodies literally right under our noses that could satisfy humanity's needs and its quest for life. And it's definitely not Neera, Mercury, or Neptune. And of course, not the gas giants. But you're getting warmer. We won't keep you waiting much longer. We're going to talk about the distant possibility of colonizing the moons of Jupiter, Saturn, and Neptune. Since school, we've known that a lot of small celestial bodies orbit around them. Some of them have long interested scientists as potential places for humanity to relocate. Don't think that paradise awaits people there. The human body is adapted exclusively for living on Earth, and even then, not in all of its regions. In very harsh locations, lacking proper equipment means a person may die instantly or painfully. But we have technologies developed over centuries, and perhaps one day they will save us. Let's start with Jupiter's moons. But are we really going to consider all 80 plus objects? Of course not. We only need to look at the 4 main ones: Ganymede, Callisto, Io, and Europa. Let's start with Ganymede. This moon isn't just big, it's the largest in the entire solar system, even bigger than our Mercury. The positive features of this celestial body don't end there. It has a magnetosphere, and that's very valuable, especially next to such a radiation abuser as Jupiter, because it means that Ganymede will be able to fend off deadly attacks and at least partially protect the modules of our bases and the colonists themselves. On Ganymede, the Galileo probe found a salty, deep ocean beneath ice layers harder than diamond. Perhaps unknown forms of life inhabit these oceanic layers. On one level of the global ocean, there might be a peculiar kind of plankton, and on another, some sort of brine shrimp like Artemia. By the way, it's this paste made from these creatures that future colonists will be able to eat, since it can replace meat. Thus, Ganymede, with its extremely thin but still present atmosphere, is quite a promising place for humans to inhabit. With the development of appropriate technologies, it is theoretically possible to extract modified oxygen from the atmosphere, which could later be used for the colonists to breathe. But it should be noted that Ganymede is extremely cold, about minus 180 degrees Celsius. What about Callisto? It is sometimes considered the top candidate for humanity's new home. This moon is geologically stable, which is very good for building a colony. The second advantage is that it's located outside Jupiter's radiation zone. Callisto is a real treasure trove of ice, from which you can not only extract water, but also process some types into fuel. For our ships, these aren't just words. In 2007, a strong year, an unmanned mission is planned to explore Jupiter's moons, including Callisto. It is considered a prerequisite for a manned flight, which will serve as the beginning of the colonization of one of these celestial bodies. But what about the other moons, such as Io and Europa? That's what we'll talk about now. The thing is, Io is quite a problematic object due to its very active tectonics. Back in the 1970s, the Pioneer 11 probe was the first to study this celestial body. Io is a very dense moon, made up of silicates and iron. But it is this Jovian moon that is more exposed to the radiation impact of its giant gas neighbor than the others. The probes that tried to study it firsthand experienced what it's like to be in a deadly embrace. The equipment here is simply inadequate, unable to operate normally, and only the Voyagers, equipped with more advanced technology, were able to observe Io in more detail. The volcanism on this celestial body has a logical explanation. Its proximity to Jupiter causes constant movement and heating of the rocks inside the moon. As a result, volcanoes appear, erupting streams of sulfuric acid. But lava tubes, which form during the cooling of magma, could very well be home to microorganisms. On the other hand, 400 active volcanoes, one of which is twice as high as Everest, make for a rather dangerous neighborhood for essentially defenseless colonists. Therefore, if humanity does decide to settle on Io, it will have to follow the example of bacteria and hide beneath the surface of the celestial body. Moreover, to build catacombs, it is necessary to find an area with a minimum number of volcanoes, ideally none at all. If this factor is not taken into account, then in just a few years the colony will be flooded with iron sulfide and silicate rocks, thereby burying its inhabitants. But with a favorable set of circumstances, underground catacombs could significantly reduce the effects of radiation, although it would not be possible to eliminate it completely. Accordingly, the equipment that ensures the functioning of the building automation system will most likely operate with critical malfunctions. Therefore, Io is rarely considered as a candidate for the future habitation of Earthlings. We have one more moon of Jupiter left, Europa. Guess which celestial body in the solar system has a huge ocean beneath its surface and hundreds of hectares of icy fields with mysterious grooves, first discovered by the Galileo probe? That's right, all of this is on Europa. The other question is, do colonists actually need this? Don't rush. Draw your conclusions. The ocean is potentially liquid water, which can be used not only for drinking, but also for producing oxygen. Although perhaps this ocean doesn't contain water, but a toxic liquid, unsuitable for conversion. And besides, to reach it, you need to drill through Europa's ice for a whole month. So overall, colonizing Europa is a very costly and troublesome endeavor. Besides, it's not safe because the low gravity will gradually lead to immune system failures and muscle atrophy in the colonist. Like those on Io, people on this moon must hide not underground, but beneath the ice to shield themselves from Jupiter's radiation. It might seem, given what's been said, that colonizing Europa is absolutely hopeless, but that's not entirely true. To begin with, we need to send a reconnaissance mission to this moon to collect samples from the subglacial ocean. But the ice on Europa is 150 kilometers thick. How can we do that, you might ask? Astrophysicists have a plan. With telescopes, scientists found geysers, showing the ocean breaks through the surface in certain areas. This means that if we fly over the surface of the moon, we can collect samples and by analyzing them, understand exactly what this huge reservoir is filled with. And as for whoever lives in it, someone similar to the inhabitants of the Mariana Trench, or even more exotic creatures. A special probe, which is planned to be launched under Europa's ice, will be able to detect them. But for now, dreams of icy cities on this moon are a bit premature, if only because each colonist here would receive a daily dose of radiation 2,000 times higher than the annual norm on Earth. What other worlds should we consider when choosing our potential new home? For example, it could be Triton, Neptune's moon, which according to astrophysicists also has an ocean beneath its several kilometer thick ice. Many people consider this choice, to put it mildly, strange, since Triton is the coldest object in the known universe. A temperature of -235 degrees Celsius has been recorded on its surface. That means terraforming the moon by trying to warm it up, as is planned with Mars, is unlikely to succeed. And besides, we still have to get to that problem because it takes an incredibly long time to reach Triton, about 12 years. And that's one of the main problems in the early stages of colonization. Even if a miracle happens and the first crewed expedition lands on Triton, it will be very difficult to supply it with materials. And solar energy is also unavailable in this extremely remote location. In short, just complications. So, which object in the solar system is considered the most suitable for colonization? It's Saturn's moon, Titan. At first glance, it's a very gloomy and cold world, shrouded in a thick layer of clouds made of hydrogen cyanide. It's like a miniature Venus. The atmospheric pressure on Titan is slightly higher than on Earth. Therefore, an astronaut would feel a pressure equivalent to being about 5 meters underwater. But this moon has the most important thing: 4 elements necessary for life: carbon, hydrogen, nitrogen, and oxygen. The only thing missing is the 5th, a human. Titan is very rich in hydrocarbon deposits, and that's a source of energy for future colonies. Radiation isn't a big threat here either because of the very dense atmosphere, although it's poisonous to humans. So it's unlikely you'll be able to go outside without a spacesuit, and the temperature won't allow it either. On Titan's surface, it's minus 180 degrees. How do we know this? In the last century, no probe could penetrate the thick layer of the moon's atmosphere. But in 2005, Huygens finally landed on Titan's surface. It turned out that there's complete darkness there because not a single ray of the scarce sunlight can break through the thick clouds. Huygens also discovered that on Titan, hydrocarbon whirlwinds rise up, gathering into dunes, just like on Earth. There are no familiar mountains here, only huge blocks of ice. In the ocean, which may be beneath Titan's crust, extremophiles could live, and on the surface of the moon, rivers of methane and ethane flow. Why rivers? Because these gases have turned into liquid in the incredibly cold climate. A scientific journal reported that cyclopropanoidine, a carbon-based organic compound usually only seen in labs on Earth, was discovered in Titan's atmosphere. It is unknown how this substance does not break down on the cold moon. It is assumed that somewhere there is a source generating heat, allowing the molecules to remain viable. Moreover, it is possible that Titan is even inhabited by some exotic forms of life, such as glacier worms. But we will only be able to find this out in 2027. That's when National Aeronautics and Space Administration is planning the Dragonfly mission. The quadcopter is expected to reach the moon around 2034. Futurologists who are thinking about establishing a colony on Titan have specifically mentioned aircraft in the form of ships and balloons, which the colonists will use to get around. But Dragonfly will do this in a relatively different way. The drone is supposed to fly at least 175 kilometers above the surface of the moon. That's when we'll see who lives on the shores of the methane lakes. In short, Titan, considering its huge reserves of important elements, seems to scientists not just the best place to build human colonies, but almost the center of the future world economy. Why don't we consider objects like Mercury or Venus for colonization? The answer is simple. In another 5 billion years, our sun will turn into a white dwarf. But first, it will become a red giant and simply burn up the first 3 planets of its system, including Earth. By the way, this is one of the reasons, along with the finite resources, why we are looking for a new home, although it's not the only one. And which of these objects would you choose as the cradle of future life? The Hubble channel won't respond for now, but viewers are welcome to share thoughts in the comments. And don't forget to subscribe if you haven't done so yet.